Welcome friends to the Formula Engineering classroom, and in this lecture of kinematics of fluid we will try to understand the concept of streamline, pathline, streak line, and two very much important topic, that is stream function and potential function. These two topics are very much important from the GATE, IES and PSU examination, and also these two topics, that is stream function and potential function, are very much interesting functions, and we will see how they are playing their roles in the fluid kinematics. So first, when we are trying to define or try to understand the streamline, pathline and streak line, why we require them? So simply we required these flow patterns to understand the types of flow and how we can analyze these flows. Like we can say that there is, to analyze the laminar flow we require streamline, to analyze the turbulent flow we use the path lines, and so on. So that's why we require this one. So let's first try to understand what is a streamline. So we can say that a streamline is a line which is tangent everywhere to the velocity vectors in the flow field. Means that I'm saying this is again, a streamline is a line which is tangent everywhere to the velocity vector in the flow field. So how can we understand this one? So that first we try to define this one, streamline, that is streamline. So let's suppose we are considering this line. Okay, so we are defining this line is a streamline. So when we say this line is a streamline, so I'm defining streamline is a line which is tangent everywhere to the velocity vectors. Means if I'm saying that there is a velocity vector here, v, some particle is moving with this velocity, there is some velocity vector here, there is some velocity vector here, there is some velocity vector here. So in this case, this line is actually tangent to this velocity vector in the given flow field. Okay, and this is instantaneous. Means when you see the flow suddenly, then you will see this line. Actually you can't see this line, this is an imaginary line, but this is not time taking phenomenon, this is instantaneous phenomenon. So this line is used to define the laminar flow. In that case, these lines are tangent to the velocity vectors. That's why the laminar flow is also defined as streamlined flow. So how can you provide a definition for this one? So in this case, let's suppose if we are considering a segment of the streamline here, we are considering a segment here. Okay, let's suppose if I'm saying this segment is of amount ds, and this velocity vector we are saying this is v here. Okay, so I'm drawing again this one, this part here, let this is here. So we are saying this section we are considering, this part we are considering, this is ds, and here is the velocity vector, let we are saying this is the velocity vector v here. Okay, now so the definition of streamline can be given like that, that is the cross product of v velocity vector cross ds. Okay, and we know when we are doing the cross product, we can write this is magnitude of v multiplied by magnitude of ds, and the angle between this one, these two, the angle between the ds and this v, we can say theta here, we are saying theta here, so we can say this is sine theta. Okay, when we are doing the cross product, then we can define the cross product like that. Obviously when we are saying this line is tangent to these velocity vectors, in that case the angle between velocity vector v and ds is 0. So as theta we are defining is 0 in this case, then we can say that there is, obviously this whole term is going to be 0 because sine 0 is 0. So we can say that there is v cross ds is equals to 0. Okay, now if let's suppose if you are saying, or when we are saying this is v cross ds, so v is the velocity vector, so we can write v is like, v is velocity components in x direction is u, so this is I cap, similarly v j cap and w k cap, as we discussed in our previous lectures. And ds we can define like, this is dx I cap plus dy j cap plus dz k cap. Okay, we have defined this one. So when we are doing the cross product, so when we are writing there is v cross ds, so vector product we can write like that, this is I, J, K here. Then for V we can write U, V, W. For ds we can write dx, dy, and dz. And we are saying for the streamline this is 0 here. So let's do the cross product here. So when we are doing the cross product, we can write this is, so we are taking first I here. So when we are taking the I, we are leaving this column, leaving this row here. So we are defining that is v dz minus w dy, then minus j when we are taking the j here. So leaving this column and this row, we are saying u dz minus w dx, and plus k cap we are saying, so we are leaving this row and this column, so we are saying u dy minus v dz. Okay, and this whole term is equals to 0. Okay, now so when we are saying this whole term is equals to 0, so for this whole term should be equals to 0, every term here should be equals to 0, because if let's suppose if I'm saying this only term is 0, so in that case the whole term is not going to be 0. So the whole term is going to be 0. In that case the all three terms should be 0 here. So from here we can write, to satisfy this condition, we can say v dz minus w dy equals to 0. So by the use of this one, I think we can write this is v dz equals to w dy. Okay, or we can say that this is v by dy equals to w by dz, or let reciprocating this one, so I'm writing this is dy by v equals to dz by w here. Okay, when we are saying the first term is 0. Now when we are saying the second term is 0, so we are saying u dz minus w dx equals to 0. So from here, like this one, we can write this is dx by u equals to dz by w. Okay, and for third term we are saying u dy minus v dz equals to 0. So by using the same concept here, we can write this is, sorry, this is v dz, this is v dz. I think there's a problem here. I think in this case we are taking k here, so this is u dy and v dx. This is dx actually. This is dx. This is dx. Okay, so we are saying this is dx by u divided by, or sorry, equals to dy by v here. Okay, so we have three equations here. One is this one, that is dy by v equals to dz by w, then dx by u equals to dz by w, and dx by u equals to dy by v. So by using all three equations, we can say that, or we can write that is dx by u equals to dy by v equals to dz by w, and this is defined as streamline equation. Okay, this is, we are defining streamline equation. Streamline equation. Okay, I think point is clear. So this is how we can define a streamline. There is one more point I want to tell you, that is two streamline will never intersect each other. Means we are saying, let's suppose if we are saying this is one streamline and this is another streamline. So in this case we are saying these two streamlines are intersecting at this point. But this is not possible. Two streamlines can't intersect each other. Why? First of all, I'm saying this is instantaneous phenomenon. Streamline is a instantaneous phenomenon. It is not time-taking phenomenon. So let's suppose if we are considering this point, or this is a fluid particle that is on this streamline. So obviously streamline is tangent to this velocity vector here. So we are saying this velocity vector is this one here. We are defining this is the velocity vector in this case. Okay, now same point we are saying, if on this streamline, then for this case the velocity vector will be look like this one here. So means we are saying if two streamlines are intersecting, each other, in that case a single particle at a same instant has two velocity vectors in different direction. Okay, means when we are saying two streamlines are intersecting each other, in that case a single fluid particle has two different velocity vectors in two different direction at the same time, and this is not possible because a fluid particle at a particular time has a single velocity vector in a particular direction. So means two streamline will never intersect each other. You have to remember all these things, that is two streamline will never intersect each other. I think point is clear. Now next we will try to understand the path line concept. So second we are saying path line. So how can you define a path line? So path line is the line or locus of a single fluid particle over the time interval during the course of motion. Means what is the sense? Means we can say that path line is the line traced by the single fluid particle when it's moving over the time interval in the flow. So if we are saying this is the path line, in that case actually this is the locus of fluid particle, of single fluid particle. They are not multiple particle, it is a single fluid particle that is moving in the flow over the time interval. Let's suppose we are saying t. So this is the path traced by the single fluid particle during the course of motion. This is defined as path line. So in this case we can say that there is two path line may cross each other. Why? Because we can say that as we are defining, first of all, path line is the locus of a single fluid particle over the time interval. So if you are taking two different fluid particles, and let's suppose if I'm saying this is some another path line, so obviously in this case this is the path traced by some another fluid particle over the time interval during the course of motion, and it is possible at one particular time two particles are tracing the same point. Okay, so means we can say that yes, two path lines can cross each other, but two streamlines never intersect each other. So this type of pattern is defined or used to define the turbulent flow system. So in the turbulent flow, in this case we can say that the particles are going to be the layers, or we can't define the layers, actually the fluid layers are exchanging energy. In that case the particles are moving up and down in the transverse velocities during the motion. So path line is basically used to define the turbulent flow pattern system. Third we have streak line. Third we have to define streak line. So what is a streak line? So I'm taking an example here. I'm taking cigarette smoke example here. Okay, in this case we are saying there are some smoke pattern here. So these lines are the streak line. So how can we define a streak line? Streak line is the line defined by the fluid particles that moved through a predefined point, means, or that passed through a predefined point. Means in this case we can say that over this line all the smoke particles are passed through this single defined point here. So they are forming a pattern over here. So in this case a number of fluid particles are involved to define the streak line. Okay, in this case the number of particles are involved and all the particles emerged and passed to the predefined point, like in this case. So this line is defined as streak line. So how can we differentiate between the streak line, path line and streamline? So streamline we defined, streamline is the line tangent everywhere to the fluid particles. So obviously in this case a number of particles are involved, but this is instantaneous phenomenon. Okay, Now in case of path line, there is only single particle is involved, and this is time taking phenomenon. Now in case of streak line, number of particles are involved, but this pattern is formed over the time, means this is also time taking phenomenon. So streamline is a instantaneous phenomenon and streak line is a time taking phenomenon. So means all three lines are different, but there is a point here, means with that point we can define here, you can make a note here. If we are defining, if flow is steady, then streamline, path line and streak line are coincide. Okay, we are saying, this is a note here, if the flow is steady, then the streamline, path line, streak line are coincide, because as we are saying the flow is steady, means there is no change with respect to time. So as streak line and path line are the time taking phenomenon, so obviously in that case the position of the particle is not going to change with time, and obviously in that case streamline is an instantaneous phenomenon, it's not depending on the time, so all three are going to be coincide in that case. Okay, so I think the point is clear. Now next we will discuss the stream function and potential function. So first let me try to understand what is stream function is. So first we will try to understand stream function, and the notation is used for this one is psi. So what is the definition? First we'll try to understand what is the definition is. So definition of stream function is such that it's it's derivative with respect to x. If I'm saying this is derivative with respect to x, provide the velocity in negative y direction, that is minus v, and its derivative with respect to y, provide the velocity in positive x direction. So what is the sense of this term? Actually this is the universal definition, and some authors are using different notations also, that is its derivative with respect to x is providing velocity in positive y direction, and its derivative with respect to y is providing negative in x direction. That is also correct. We'll see how this is correct. That is correct. And let first we try to understand this one. So what is the sense of this term, why we are defining, and what is the use of this function? So actually there is no physical significance of this term, but this is a mathematical trick. In this case, some higher order function psi is combining two lower order functions u and v. It is such that is its positive, so its derivative with respect to x provide the velocity in y direction, and its derivative with respect to y is providing positive velocity in x direction. This is the definition provided by the books and authors, but we will try to understand what is the sense of this term. So without considering this one, we are simply saying psi is some function. Psi is some function of x and y. Okay, it's simply a function. So I think we can easily do what is the total derivative of this one. So we can add the total derivative of this one will be del psi by del x dx plus del psi by del y dy. This is the total derivative in this case. Okay, now so let's suppose if we are saying psi is constant. Okay, we are saying if psi is constant, so in that case we can say that the change in this function is going to be 0. Obviously when this is constant, then there is no change in this one. Okay, so from this one we can write or rewrite this equation like, that is del psi by del x dx plus del psi by del y dy equals to 0. Okay, now this is obviously 2D function, this is lying in x and y only. Now let recall the streamline equation in 2D. So we write equation, streamline equation, that is dx by u equals to dy by v here. Okay, and let again we are rewriting this one, and we are simply saying this is v dx minus u dy equals to 0, we can say this one, or we can say that this is u dy minus v dx is 0. Okay, so there are two forms. We can write simply, this is, I'm multiplying the negative sign in the whole equation, so this is going to be positive and this is going to be negative here. So by comparing this equation and this equation, the term with dy is u here, here is u, the term with dy, and here the term with dy is del psi by del x. So we can say this one, this u is equals to del psi by del y. Now here the term with dx is minus v, and here the term with dx is del psi by del x. Okay, so you can see this one. So actually we are comparing these two equations. One is the equation for the streamline, another equation we are simply defining a new function here. So we are defining this function is such that is this function derivative with respect to y provide the velocity in positive x direction. Its function derivative with respect to x provide the velocity in negative y direction. I told you that is some authors are also writing this one like that. That is del psi by del x is v and del psi by del y is minus u. There is also no problem in this case, because when you compare this equation to this one, you will get this expression. Okay, now so this is the equation basically, but what is the sense now? We are saying stream function is such that is it remains constant and there is no change over here, and then we are getting this equation, means we can say that is stream functions remain constant for a streamline. Okay, we can say that there is some function that we are defining a stream function that will remain constant for streamline, means the function is not going to change over the streamline. So if we are, let's suppose we are defining here sets of streamline for a flow. In that case, for a particular streamline, the particular stream function is constant throughout the line. So for this one, let I'm saying this is psi 1, it is remain constant throughout this one. For let's suppose this is psi 2, so it is remain constant over here. Similarly, psi 3 remain constant third streamline, and psi 4 we can say that this is remain constant over here. Okay, so through this function we can identify individual streamline in the set of streamline, or when we are saying stream tube. What is the sense of stream tube? So stream tube is a group of streamlines. So let imagine there is some flow of water from a tap. So when there is a flow of water from a tap, then it look like a tube. We can say it look like this one. Okay, there's a tap over here and there's a flow over in the downward direction, so it is look like this one. So in this case, this is defined as stream tube. This is defined as stream tube. Okay, and this is formed by number of streamlines. You can imagine a broom, and that broom, every broomstick is one streamline. It's like that. So means for particular streamline, a stream function remain constant. So if I'm saying over this one, for this streamline, let's suppose this is psi 1, so this is also here psi 1, it is not going to change over the streamline. And around here, when we are saying we are counting the streamline, so let's suppose for I'm saying psi n, so for this streamline this remain psi n, as we are saying there are n streamlines here. So in this case, for a particular streamline, there is a particular stream function. So from here we can say that is stream function is that function which remains constant along a streamline, and that is not going to change along that line. And this concept is very requirement, or very important concept, because we will use this concept in case of Bernoulli equation. Okay, so I'm saying that is stream function is a function that remain constant along a streamline. Okay, so the definition of streamline in 2D we can provide this one. that is dx by u equals to dy by v, and for that one we can say that for a particular streamline, stream function remains constant. So this is the one sense of this one. What is the another one? So let's suppose I'm saying in this case, first I'm defining this one. First we provide the definition here. So what is the second sense? So let's suppose we are considering a continuity equation for a 2D flow. I know I don't tell you what the continuity equation, but hope you know the continuity equation for the 2D flow. We will discuss it after this lecture. So for 2D flow, for actually incompressible steady 2D flow, continuity equation we can write del u by del x plus del v by del y equals to 0. This is the continuity equation for incompressible steady 2D flow we are defining here. We will discuss it later after this lecture. Okay, in the next lecture I will tell you how we can drive this equation. So in this case we are considering directly here. So del u by del x plus del u by del y equals to 0 is the continuity equation for incompressible steady 2D flow. Okay, so from our definition of stream function we know the value of u and v. So we can put the value of u and v in terms of psi here. So we can write this one like, so we are writing the value of, we are putting the value of u here first. So we are writing this is del 2 psi by del x del y, then minus, we are putting the value of y here, so that's why there is negative sign. So we can say del 2 psi by del y del x equals to 0. Obviously both these two terms are equal, so they will going to be cancelled out. Means the stream function will always satisfy the continuity equation. So from here we can conclude that if stream function exists, then the flow will always be exist and it will be continuous. I'm saying if stream function psi exists, flow will always be continuous. Okay, or the flow will always be exist here. Okay, because it will always satisfy the continuity equation. So if the stream function is existing, in that case the flow will exist and the flow will always be continuous. This is our second point. So let's check our third point about the stream function. I told you that stream function is very much important function, and this is very much important topic from the GATE, IES and PSU examination for all the engineers who are appearing according to their branch. Now third, let's suppose if I'm saying for, or let we are taking rotational equation for 2D flow. So we discuss in the rotational flow that is omega z is equals to del u by del y, or actually this is, I think we discussed, that is 1 by 2 del v by del x minus del u by del y. Okay, we discussed this equation in the rotational flow. So omega z is what? This is the rotation of fluid about z-axis. Means if in this case if I'm saying this is our plane here, this is our x-axis, this is our y-axis, here is our fluid element here in that case. So this axis is actually z-axis we are defining here. So we are talking about the rotation about z-axis. Actually this rotation in the 2D plane. That's why I'm writing this equation, that is omega z equals to 1 by 2 del u by del x minus del u by del y. Okay, let's put the value of u and v here. So we can write this is 1 by 2, this is minus del 2 psi by del x square minus del 2 psi upon del y square, when we are putting the value of u and v in this equation. Okay, so let's suppose, and let we am saying if omega z is 0, I'm saying if, so in this case del 2 psi by del x square plus del 2 psi by del y square will be equals to 0. Okay, negative sign, so we are taking here both, we are multiplying simply negative sign here. So in this case this is going to be positive, this is also going to be positive here. Now so when we are saying this is 0 means we are saying irrotational. This is irrotational flow we are talking about in the 2D system. This is Laplace equation, and we can write this one like that. There is del 2 psi equals to 0 here. Okay, so in our third point we can say that if this is our third point, we are saying this is our third point here. If psi exists and if it satisfy the Laplace equation, then the flow will be irrotational. Okay, I'm using two words here. If psi exists and if it satisfies the equation, because if it is not satisfying the equation and this term is not equals to 0, in that case the flow is not irrotational flow. So there are two conditions here. If psi exists and if satisfy the Laplace equation, then the flow will be irrotational. Means in the second point it is giving the clear indication, that is if psi exists then the flow will definitely exist and it will be continuous. But in second case it is not clear indication, but it is saying if psi exists and if it is satisfying the Laplace equation, then the flow will be irrotational flow. Okay, this is our third point about the stream function. Now let's talk about the fourth point. So for our fourth point, now select fourth point. Now that I'm considering two streamlines here. One is this one, another one in this one. So for this streamline that I'm saying, this is stream function is psi. Obviously for streamline psi remains constant. Sorry, this is psi b, not psi a. For the second, this is psi b. So for this one psi b, for this is psi a. Okay, now that we are saying this is the cross section between the two streamline, or this is the minimum distance. So obviously this line is perpendicular to these streamlines, and let we are saying this is ds. Okay, this is ds here, and let's suppose we are saying perpendicular velocity is v here. So this is obviously perpendicular to this one. So in this case we want to define what is the discharge. So for discharge we can say that discharge will be equals to v into ds. Okay, discharge will be equals to what? V into ds. When the velocity and the cross section area is perpendicular to each other, in that case we can define discharge will be equals to v ds. But now let in this case we are saying this velocity has two components, one in the downward direction, that I'm saying this is v here, and one in the horizontal direction, this is u here. So u is positive x direction, so this is positive value, but v is in downward direction, that is in negative direction, so I'm taking this is minus here. Okay, so v has two components here. Similarly this ds also has two components here. Ds, because the area is a vector quantity, so this also has two component here. Sorry, line is not straight, but no problem. So one is this one, another one is this one. So this component we can say this is dy, and this component we can say this is dx. Okay, so this area has two components, dx and dy. Now let's take a look. U is perpendicular to dy, so we can also write this discharge will be equals to u dy, positive u dy, and minus v is perpendicular to dx, so minus v is going to the dx, so we can write minus v dx. Okay, again I'm saying u is perpendicular to dy, so I'm writing u dy, and v is proportional to dx, that is negative direction, so I'm taking minus v dx. So now by that definition we can write the value of u and v here from our stream function definition. So u is del psi by del y dy, minus v is del psi by del x into dx. Okay, so this is what? This is actually total derivative of psi. So we can write this is d psi. So from here we can say that there is discharge between two streamline is the difference between the stream functions. So we can say discharge is equals to d psi here. Okay, so what is the total discharge between these two streamlines? So we can integrate this one. So we can integrate dq here, and we can also write this is integrating d psi from the stream function psi a to psi b here, because between two streamline we are considering the discharge. So by this integration we can write this is psi b minus psi a. Means what? Means if you want to calculate the discharge between two streamlines, in that case you can directly say that there is discharge between that two streamlines will be directly equals to the difference between that two streamlines stream functions. Okay, this is our fourth conclusion, that is discharge between two streamline is simply the difference between the stream function of that two streamlines. Okay, point is clear. So we made here four conclusions by the use of stream function. So stream function is a very important topic, I'm saying again, and we'll use this topic in the next lectures in the Bernoulli and other things. Okay, so guys, if you are enjoying the videos, please like the lecture, please comment your doubts, ask your doubts, and subscribe the YouTube channel so that I can carry on and my energy level is going to be up in that case if you are subscribing the channel and liking my videos. And please share the knowledge as much as you can. Thanks guys, take care of yourself, see you in the next lecture. Thanks again.